Sorry, I had a little technical glitch, so I'm hoping that this picks up from where I left off. So where was I? We were talking about the derivative of, derivative of tangent equaling secant squared. And I was telling you that it's because of the quotient rule. The derivative with respect to x of sine x over cosine x is low, d high. The derivative of sine is cosine, so that would become cosine squared on the top of there. So low, d high, derivative of sine is cosine, minus high, d low. The derivative of cosine is negative sine, so that's going to become plus cosine squared. Draw a line and square below. Now cosine squared plus sine squared is 1. And 1 over cosine squared is secant squared. So everything is not memorized. I mean, I would memorize that, but know where it comes from in case your memory fails you. The derivative of secant is equal to secant tangent, and those should get in your memory. Remember the cofunctions we didn't memorize, but they were what you thought they should be, except they had an opposite sign. So the derivative of cotangent, you might say, well, that's going to be cosecant squared. And you'd be almost right. Again, if you went and proved it or derived it using the quotient rule on cotangent, cosine over sine, you'd actually come up with a negative cosecant squared. So it is what you would think it would be. The cofunctions are not tested on the AP exam, but I pepper them throughout your work sometimes, because if you were in college, you would need to know those. The derivative of cosecant, likewise, you would think it's cosecant cotangent. It almost is. It's negative cosecant cotangent. All right. The derivative with respect to x of the natural log. Let's do the derivative with respect to x of the natural log of a function of x. Remember, if that was just x, it's 1 over x. But really, it's u prime over u, or sometimes we said it's 1 over u times du dx. What does she mean by that? I think you guys know, but just in case. The derivative with respect to x of the natural log of 3x plus 1 is u prime, the derivative of 3x plus 1 over u. Done. All right. And how about the derivative of e to the u? I'm assuming you guys were really good with derivatives. I might be boring you, but that's okay. It's okay to be bored once in a while. Is e to the u times du dx, or e to the u times u prime. So the derivative with respect to x of 3 e to the 3x is e to the 3x times du dx. Done. Right? Nice and easy peasy mac and cheesy. Tangent lines. We drilled that one in last year, didn't we? And I said, I'm 100% sure you're going to get an equation of a tangent line on the AP exam. And sure enough, everyone did. They were all different tangent lines, but I know you had one. Anyway, so by the way, the AP reading this year, we did it from our homes. The PDFs came in on the computer screen, but we still had like a reading group and a reading leader, and it was done through Zoom, and it was really cool. It's a very authentic process. I think your scores actually are pretty representative nationwide. The national passing rate was about the same as it always is. We in BC last year had 100%. I was hoping for all 5s, actually. I thought I had a crew, but I had 2 3s and 2 4s, and then 28, I think, 5s or something like that. But they rocked it. They did really well. You guys will do the same this year, I'm sure. I'm confident in you people. So let's go take a look at this guy. So remember, when we write an equation for a tangent line, let's review. We do our tangent line to the curve at a point. The equation for any line, we need a point and we need a slope, but the slope in this scenario is the derivative. Remember, that's what a derivative is. It's the slope of the tangent line. So what we need for the equation of a tangent line is a point. If they just give you the x, right, then you plug it into the function to get the y. And we need the slope, but the slope is that derivative at that point. Okay, then we write y minus the y we know is equal to the slope there, the derivative, times x minus the x we know. And we drilled that in so much last year. So if your function was, say, let's just do a parent function for a quadratic, y equals x squared, or f of x equals x squared. And if I said write the equation for the tangent line to the graph at x equals 3, I would need the point where it hits, and that would be at 3 comma 9, because 3 comma 3 squared. I'd also need the slope. Well, the slope is the derivative. The derivative of x squared is twice x, so I'd have to, for the slope, double the 3, it'd be 6. And then I'd write y minus the y I know, in this case a 9, is equal to the slope there, 6, times x minus the x I know. So that would become the equation for my tangent line. All right, remember for tangent line approximations, back and erase that. And again, if you're writing these in a notebook, that's just fine as well. I kind of think the derivative review should be a lot better for you than the limit review, but because you guys rocked derivatives last year. But let's suppose we had a function, and we'll call it f again. And we wanted to use the tangent line to approximate what happens on the curve. As we move farther and farther from the point of tangency, our error is a lot more. Like the actual value on the curve versus the one on the tangent line, there's a pretty big gap here. But as long as we stay close to the point of tangency, we should have a pretty close match between the point on the curve and the point on the tangent line. Now this year in Calc BC, it gets a lot cooler. We have two far better ways, because this tangent line approximation, honestly, they're only good if you're really close to the point of tangency. So later in the year, we're going to do something called Euler's method. That actually comes earlier in the year. And then towards the end of the year, we're going to be actually fitting curves to approximate. So it gets really cool. But the tangent line from AB, you'll realize how weak of an approximation this is once you get to the better ones in BC. But it says you just need the point, right? You need the slope there, which is the derivative. But then you get your equation for the tangent line, and if this was at 2 and you were estimating what happens at 2.1, you just plug 2.1 into your equation for the tangent line. So I don't know that we need to talk a whole lot about that. Another thing that you guys were really strong with was this increasing D. You got really good at graph analysis, but let's go back and talk about a function is increasing. Its first derivative will be positive. If a function is decreasing, its first derivative will be negative. If a function is concave up, its second derivative will be positive, or equivalently, its first derivative will be increasing. Those are equivalent statements, because if a function's increasing, its derivative is greater than 0, and the derivative of f prime is f double prime. A function is concave down when its second derivative is less than 0, or equivalently, when its first derivative decreases. We have a maximum when the first derivative changes from positive to negative at, oops, that shouldn't say 0, positive to, pardon me, it's really hard to write with this stylus, but I like being on the iPad better than up at my smart board. So changes from positive to negative at a critical value. Remember, a critical value is where the derivative equals 0 or doesn't exist. Kind of important, because this cusp right here very well may be the maximum of a relative max or an absolute max of the function, but the derivative doesn't exist there. So make sure you remember those critical values are where the derivative equals 0 or doesn't exist. Same with minimum. we would say f prime changes from negative to positive at a critical value. You can write that down. You can always pause these. So f prime changes from negative. Remember why? If f prime changes from negative to positive, f went from decreasing to increasing. Because remember, derivatives are slopes. F prime right here is negative, the slope's negative. F prime right here is negative. Oop, F prime is 0, critical value, and then went positive. So we would have F prime changing from negative to positive at a critical value. Cool, right? And inflection points. Inflection points occur where the second derivative changes sign. So we need F double prime to change sign. Remember, that's equivalent to f prime changing from increasing to decreasing. Again, I can't fit that with this small stylus over there. So after that, we did a little implicit differentiation. Remember, explicit is something where f of x is defined explicitly as a function of x, 3x squared minus 2x plus 1. And its derivative would be 6x minus 2, or its derivative with respect to x is, I can do each of these terms separately. You know, if I were to say the derivative with respect to x is equal to f prime is 6x minus 2, the derivative of constants go to 0 because the slope of a constant function, horizontal line, is 0. Lots of derivative stuff in here, right? There's a lot to review. It was months for us last year, but again, a strength of yours. So on an average. So we'll see how it goes. If we need to add more days later, we will. So implicit means that y is not a function of x. It's when we have these x's and y's mixed together, often on both sides of the equation. And you might say, well, I'll just solve it for y. That's often tedious or not even possible. So what we do, let's see if you remember. I would love it if you'd pause the video and see if you remember yourself. But we're just going to go start and say, well, we take the derivative with respect to x of both sides. And this was one of the rare occasions where I allowed you to use the prime notation instead of what we call this Leibniz notation because it was so cumbersome. So, and I'll hold with that. So remember, if I take the derivative of a product, I don't do the product of the derivatives. I do the product rule. So I'm going to take the derivative of the first function. No, sorry, I'm going to do first, which is x, d second. Now, using my chain rule, that would be 2y times the derivative of the guts, dy dx. So y prime. That's first d second plus second d first. Now, the derivative of x with respect to x is 1. So first d second plus second d first, right? And then it'd be minus the derivative of 2x with respect to x. And again, derivative of 2x with respect to x, the 2 comes out front, and I have 2 dx dx. It's just 2. We know that, though, because the derivatives are the slopes there. Minus 2x is a linear term, and the slope is negative 2. So that certainly makes sense. It should all tie together in your large brains. And then the derivative of 4y with respect to x, the derivative of 4y with respect to x is, constants out front, 4 dy dx, or 4 y prime. So remember with that process, we are simply applying our rules of differentiation from up above. We did a little product rule, we did a constant multiple rule, we did a chain rule in here. Then we need to isolate that y prime, because remember, we're looking for dy, the derivative, y prime. So we get it on one side of the equation. So I'm going to keep the 2xy y prime, this guy on this side. I'm going to move this guy over by subtracting it. And then I move those non-y prime terms over to the other side. So I'll add the 2 and subtract the y squared. Then I factor that y prime out with the net goal of trying to isolate it. And I get 2xy minus 4 equaling 2 minus y squared. This was fun. Isn't this fun? I love derivatives. You can tell I like them so much more than limits. But limits are necessary. I get that. So now to solve for y prime, my y prime isn't a function explicitly of x. It's implicitly defined in terms of x and y. So if I wanted to find the derivative at the point 27, I have to plug them both in, not like up here on this one where my derivative was 6x minus 2, it's just explicitly in terms of x. So if I said, what's the derivative of 4, you'd go 24 minus 2. With implicit, you have to have both coordinates to plug it in. Usually implicit functions graphically they're actually not functions. They're usually kind of like that. And when you're finding the derivative, you're finding the slope at a specific spot. Remember, if it said, where is there a vertical tangent line, we'd want that derivative to be undefined, or we'd want this denominator to equal 0. For a horizontal tangent line to implicitly defined curve, we would want the derivative to equal 0, or the slope of the tangent line to be 0. So we'd set the numerator equal to 0. So keep that in mind as well. And then everybody's favorite, our related rates. You might say, I need to know all of this today. No, we're just going to get some of the, just this first page down, and then we'll continue. You just need the notes for by Monday, and then Monday we'll go start to kind of plug our way through that skills review packet and do some examples in class. Right now we're just sort of bringing back some of these basics. You definitely, it's totally understandable that you might have forgotten some of this stuff. Don't worry, it'll come back. So with related rates, those are rates that are related to each other. You always kind of know when you're working with a related rate because there's two or more things changing at one time. So as the volume is changing in the swimming pool, right, so is the height of the water in the swimming pool. The radius stays constant. But if it was a cone, as it fills with water, the volume of the water increases. The radius is also increasing, right? And the height is also increasing, and they're all related to each other. Remember our process, and we'll do an example or two of these in class. I just want to remember you need to have yourself a good picture when you start these. And then we always ask ourselves, well, what do we know? All right, they always give you one rate of change. Like they'll say, you know, the height is changing at a rate of -2 centimeters per second. Keep in mind, because the height is changing at a negative rate, it means the height's going down. So that would be something leaking oil or leaking water. But we always ask ourselves, you know, what rate do I know? We always need an equation that relates the variables in the problem. So if we're dealing with volume of a cylinder, we always write down that pi r squared h. They have to tell me how this is changing or how this is changing, or how they have to give me one, like, what do I know? All right. Once we have that equation, we take its derivative. But remember, it's changing over time now. So we take the derivative of it with respect to t. And we'll practice later. And then when we're done, we plug and solve. And that actually, I'm not doing a sample of right now, I don't think, unless, let me go check here and see if I have yeah, let's go try it. Let's go take a look here at this area of a square, just in case you're like, yeah, I need a little more on that. Let's just do a real basic one here. So it says the area of a square is expanding. So I'm going to draw myself a square. Its area is expanding. So I'm going to do little arrows. This is number 1, get yourself a good sketch. At a rate of, there's one of the rates you were given. It's the rate that the area is changing over time. So I'd immediately go down what rate I know. I know dA dt is, and it's expanding, so it's growing, so it's positive. Find the rate at which the side of the square. So I'm looking for ds dt, let's call that s for side. At the instant when the area is 16. This is what I'm trying to figure out. So I was like, well, what do I know? What am I trying to find? The next step we said is to get an equation that relates the variables. Well, the variables are A for the area and S for the side of the square. So our equation for this guy is going to be A equals S squared. Now what do? We take the derivative of both sides with respect to t. So on the left, we do dA dt, the rate that the area is changing, is equal to 2s times the derivative of the guts, ds dt. Now, what am I looking for? I'm looking for ds dt when the area is 16, okay? Well, dA dt was given, so I'm going to go, oh, dang, man. So I'm going to say 120, that was given in the stem of the problem, is equal to 2 times s times what I'm looking for. So there's got to be a way I can find s. How can I find s? They gave me the area of the square. If the area of the square is 16, the side length is 4. So I would do 120 over 8. Simplify it is ds dt. But remember to get that label. So I'm just going to write 1/28 for now. Is equal to ds dt. To determine your label, you say, well, what are the sides measured in? Well, if the area was centimeters squared, that'd be centimeters per. What's my unit of time here? Minutes. So it'd be 128. You could simplify it if you want, 15 centimeters per minute. So last up, I think, because I don't want this video to be too, let's just stop right here with the MVT. All right, and I'm not going to give you homework. If you want to start putzing at it, you can, but we're moving into derivatives starting Monday. This is just some pre-notes that I want to get out of the way over the weekend. So let's go talk about our mean value theorem. What did it state? Well, first of all, there was a hypothesis that had to be met, right? You can't even use it. Like if I were to say, if you're wearing green and play football, you get an A for me. No matter what happens. You immediately look down and make sure both parts of that hypothesis are met because of that word and. So if you're wearing green and don't play football, sucks for you. If you're not wearing green and you play football, still sucks for you. If you're not, both of them still sucks for you. But if you're wearing green and you play football, you go score. I can take the conclusion and apply it to myself. So that's how these existence theorems work, if you remember. The hypothesis has to be met in full. And the hypothesis for the mean value theorem is that the function must be continuous and differentiable. Remember, if it's just continuous, that doesn't cut it. So if it goes like this and then there's a cusp or whatever, that I can't apply the mean value to on any interval that contains that place where the derivative doesn't exist. If the function's differentiable, however, differentiability implies continuity. I said to remember Diet Coke. If they tell you it's differentiable, they need not tell you that it's continuous. But if it's continuous, they have to tell you that it's differentiable. Here's a continuous function, the absolute value function, that is not continuous on an interval containing its vertex. So they have to at a minimum tell you it's differentiable, or they have to say continuous and differentiable. If a function's continuous and differentiable, what the mean value theorem says is that on any given interval on which the function's continuous and differentiable, there has to be at least one place where the average rate of change or the slope of the secant line, and I told you guys to write msec. I said, the minute you see that mean value theorem, think m's for slopes, where the average rate of change or the slope of the secant line has to equal the instantaneous rate of change or the slope of the tangent line. That has to happen. Your average change has to equal your instantaneous rate of change, at least one point on that interval. And I think when we talked about this, we used temperature, and I think we also talked about like when you're driving. Your average speed, at some point, if my average speed on the way to work is 70 miles per hour, that average rate of change, it'd be the slope of the secant line over the course of my drive to work. At some point, I had to be going at least 70 one time. Otherwise, as I was under it or I was over it, like there has to be a place where my instantaneous rate of change was also 70 degrees. Same with temperature today. If the average temperature ends up being 52 degrees today, there has to be a time, at least once, where the temperature was 52 degrees. All right, so now how do we put that in terms of a formula? Well, the average rate of change of a function is the slope of the secant line. It's the change in y. So if this is the point b, f of b, and this guy over here is the point in yellow, a, f of a. We know that the change in y over the change in x is how we get slope. So we say y2, f of b, minus y1, f of a, over b minus a has to be equal to the slope of the tangent line. The slope of the tangent line is the derivative. So it has to equal f prime at some place. And I told you guys you can call it x. If you Googled it, it'll say f prime at c. It guarantees the existence of at least one spot. So it's the c that you're finding. The one spot where the slope of the tangent line will run parallel or be equal to, I'm sorry, the slope of the secant line. So that's as far as we're going to go today. And when you come in on Monday, I'll probably, I think, record while I'm teaching that hour, because I'm going to be asking you guys some questions about this. Or I'll have you log on and take like a little Schoology quiz on it. I'm not quite sure yet. By Sunday, I'll have next week's schedule all laid out. I have to monitor last year's just due to our distance format that we've got going on. But I know for sure on Monday, we'll be finishing up these notes and examples with derivatives. And we may start moving into an assignment for it as well. But for this weekend, Friday, Saturday, Sunday, you should have played the quizzes. I'm going to put that in as a full score. So if you don't get what you want, I think I set it to go twice. So take it twice. Also, you should have these notes. So I think I'll probably have you upload a picture of these notes on a Google form too, just to make sure we've got them. And you guys have a great weekend. I hope everything's going well. Feel free to hop into my Google Meet today if you're up on time, if you need any help. If you've watched this on time, or, seek help, not seek help, like seek help, not seek help. See you later, guys. Have a good one. I'm gonna stop recording here if I can.